Hello everyone, this is Avelino Dawes, your instructor. In the previous lecture, we considered the positive, negative, and sequence representations of our generators, transformers, and transmission lines. Now, this time we will consider an example. Here we have a power network wherein we have generator 1 connected to bus 1, and generator 1 is solidly grounded, and from bus 1 to bus 2, we have transformer T1, which is YY connected, both grounded solidly on both sides. And then from bus 2 to bus 3, we have a transmission line, TL23. And from bus 3 to bus 4, we have another transformer. T2, and the connection is YY, not grounded. Now at bus 4, we have another generator G2 being connected, which is impedance grounded with value of impedance of J0.03 per unit. And then also at bus 4, we have transformer T4 being connected, which is delta delta connected to bus 6. Now, and from bus 6 to bus 5, we have a transmission line TL56. And then between bus 5 and bus 1, we have another transformer which is YY connected and both grounded. Now the data of the network are given here. No, for generator 1, it has an MPa rating of 200 with a voltage rating of 20, and its positive sequence reactance is 0.2, its negative sequence reactance is 0.14, and its zero sequence reactance is 0.06. And for G2, its MPa rating is 200 and voltage rating of 13.2, and positive sequence reactance of 0.2, negative sequence reactance of 0.14, and zero sequence reactance of 0.06. Now for a transformer T1, it has capacity of 200 MVA and voltage rating of 20 to 230 kV, and its positive reactance is 0.2, and its negative sequence is 0.2, and its zero sequence reactance is 0.2. No, so this is what we discussed before, that for transformers, the positive sequence, the negative sequence, and the zero sequence are equal. Now for a transformer T2, it has an MVA rating of 200 with voltage rating of 13.2 to 230 kV. Its positive sequence reactance is 0.3, negative sequence reactance of 0.3, and also zero sequence reactance of 0.3. Now for a T3, it has an MVA rating of 200 and voltage rating of 20 to 230 kV, and positive sequence reactance of 0.25, negative sequence reactance of 0.25, and zero sequence of 0.25. And for a T4, it has an MVA rating of 200, voltage rating of 13.2 to 230 kV, then positive sequence reactance of 0.35, the negative sequence reactance of 0.35, and zero sequence reactance of 0.35. Now for the transmission line, TL23 is 200 MVA with a voltage rating of 230 kV, and X1 is 0.15 positive sequence. No, and the negative sequence is 0.15, and the zero sequence is 0.3. Now TL56, the MVA capacity is 200, and the voltage rating is 230 kV, and the positive sequence is 0.22. The negative sequence is 0.22, and the zero sequence is also 0.3. Now we are required to draw the corresponding positive sequence network. Okay, and in letter B, we have also to draw the corresponding negative sequence network, and letter C, we have to draw the corresponding zero sequence, okay, network. Now, the positive sequence network shown in figure, okay, 5.13a, and then the negative sequence network is shown also in figure 5113, and the zero sequence network is shown in, okay, figure 5.13. Okay, this is the positive sequence network. Now, between bus 1 and the reference neutral, we have the generator 1, which we represent with a generated voltage per phase of 1.0 at an angle of 0 and reactance of J.2. Okay, and between bus 1 and bus 2, we have transformer 1, okay, which can readily allow, okay, the flow of positive sequence current from the primary terminal to the secondary terminal. And so we represent our T1 with its positive sequence reactance of 0.2. Now between bus 2 to bus 3, we have transmission line, okay, which is represented by its reactance of 0.15. In this case, the resistance of the transmission line is just neglected, so we have only the reactance. Now between bus 3 and bus 4, we have transformer 2, which again can allow the flow of positive sequence current from its primary terminal to the secondary terminal. And so we represent, okay, transformer 2 with its positive sequence reactance of J.03. Now between bus 4, okay, we have generator 2 being connected, and so we represent our generator 2 with its generated voltage also with a magnitude of 1.0 at an angle of 0 per unit, okay, and its positive reactance of 0.2 connected between bus 4 and okay, the reference axis N1. Now down here between bus 1 to bus 5, we have transformer 3 with YY connection. So positive sequence current can just flow from the, okay, primary terminal to the secondary terminal. And so our transformer 3 can just be represented by its positive sequence reactance of J.25. And between bus 5 and bus 6, we have transformer, okay, a transmission line TL56 with its reactance of 0.22, and the resistance of the line is also neglected here. Now, between bus 6 to bus 4, we have, okay, transformer 4, which is delta-delta connected, but the positive sequence current can just flow from, okay, its primary terminal, okay, to the secondary terminal. So this is how we represent our, okay, positive sequence, okay, network. Now this is our negative sequence network. Our generator G1 here is just represented by its, okay, negative sequence reactance of J.014. Now there is no generated voltage, okay, for our generator in the negative sequence because our generator cannot generate negative sequence voltage. So we have only, okay, this reactance to represent our generator 1, which is connected between bus 1 and this, okay, reference neutral in 2. Now for our transformer 1, okay, again, negative sequence current can just flow between bus 1 to bus 2. So we have the negative sequence reactance of transformer 2, and then between bus 2 to bus 3, we still have the transmission line, okay, which can also allow the flow of negative sequence current. Now between bus 3 and bus 4, we have transformer 2, okay, which is, okay, YY connected now. So uh, the negative sequence current can also flow from the primary terminal to the secondary terminal. So we have this, and our transformer is represented by its negative sequence reactance of J.3. And then from bus 4, okay, to the reference neutral, we have generator 2, and it is represented by its negative sequence reactance J0.14 without again, generated voltage here because for the same reason that our generator cannot generate negative sequence voltage. Now, down below, we have from bus 1 to bus 5, we have transformer 3 with reactance of J.25. And again, a negative sequence current can flow between bus 1 to bus 5. And then between bus 5 and bus 6, okay, we have transformer transmission line which can allow the flow of negative sequence current. And between bus 6 and bus 4, we have transformer T4, which is delta-delta connected, and negative sequence current can flow from the primary terminal to the secondary terminal. So our transformer T4 is just represented by its reactance J.35. So this is how our negative sequence network of the given power system okay, uh, being represented. Now for the zero sequence network, okay, for our generator, again, it is just represented by its zero sequence reactance of J.06, and there is no generated voltage here, okay, for the reason that our generator cannot generate, okay, zero sequence voltage. So between bus 1 and this reference neutral NO, we have only this, okay, reactance, now representing our generator 1. Now, between bus 1 to bus 2, we have transformer T1, which is YY connected and grounded both sides. So, meaning a zero sequence current can just flow from the primary terminal to the secondary terminal. And so our transformer is just represented by its zero sequence reactance of 0.2. Then between bus 2 to bus 3, we still have the transmission line represented by its zero sequence reactance of 0.3. Now between bus 3 to bus 4, okay, we have transformer 2 YY connected but ungrounded. So remembering our discussion on the equivalent circuit for zero sequence reactance of our transformers. So for ungrounded YY connection, okay, it is open at the primary terminal and also at the secondary terminal. So we just represent our transformer T2 with this negative zero sequence reactance of 0.3, okay, but with open connection at the primary and the secondary terminals. And then between bus 4 and the neutral, NO, okay, we have our generator 2, and our generator is represented by this zero sequence reactance of 0.06, and in series with the reactance of the grounding impedance, okay, which is 0.03 times 3. Now, remembering the grounding reactance that we have, okay, of 0.03, then since three zero sequence currents IAO, IBO, and ICO okay, flow through this grounding reactance, so we multiply the original value of 0.03 by 3, so it becomes 0.09. Now down here between bus 1 and bus 5, okay, we have transformer 3, which is YY connected and grounded both sides, so the same as transformer T1, zero sequence current can just flow from the primary terminal to the secondary terminal, and so we represent our T3 with its zero sequence reactance of 0.25. Then between bus 5 to bus 6, we have transmission line, which can also carry zero sequence current. But between bus 6 and bus 4, we have transformer 4, which is delta-delta connected. So for delta-delta connected, okay, it is open at the primary terminals and at the secondary terminals. So we have here open primary, open, okay, secondary. But since the windings are delta-delta connected, okay, zero sequence current, okay, will just circulate, okay, in this loop. It cannot go out, okay, to the primary side or to the secondary side. So it's just circulating, okay, without any effect on the rest of the network. So this is how we represent our zero sequence network. Now the previous example is extended in this case that we have to consider the power system given in the previous example, and we have to assume that there is a fault on bus 3. Okay, then we have to reduce, okay, the sequence networks, okay, drawn and the previous example, okay, to their Thevenin's equivalents, okay, looking in at bus 3. So we have to show the steps of the positive sequence network reduction, and second, we have to show the steps of the negative sequence network reduction, and then lastly, we have to show the steps of the zero sequence network, okay, reduction. So for our solution, we have, okay, the figures 514, okay, showing the steps of the positive sequence network reduction, and figure, okay, 515, okay, showing the steps for the negative sequence network reduction, and figure 5.16, okay, showing the steps of the zero sequence network, okay, reduction. So for the positive sequence network, okay, in the previous example, we have seen that, okay, this is our equivalent, okay, positive sequence network after representing our generators and transformers, okay, with their equivalent, okay, circuit, okay, with their corresponding values of reactances, and also with the representations of the, okay, transmission lines. Now, as required, okay, we have to, okay, there is a fault at bus 3, and we have to obtain the Thevenin's equivalent circuit, okay, with respect to bus 3, now looking to the circuit, okay, looking into, no, the circuit, okay, relative or with respect to bus 3. So there is a fault here. Okay, so how can we do that? So notice that we have these three reactances, okay, in series, so we can combine them together, and these two also are in series, so we can combine them together. Now, and then we have these remaining okay, reactances and voltages. So the resulting after combining these reactances, our network would then become, okay, like this, no? At the bottom here, we have the total of J 0.82, and here at the left side, we have the sum of the transformer and transmission line. So we have J.35, and this is for transformer 2. Okay, and then we still have this, okay, for generator 1, and this is for generator 2. So this is now a little bit simpler, or looking simpler, because we have combined, okay, the impedances here and also at this side. So next, okay, we noticed that in the previous slide, okay, we have formed, okay, delta connection of the reactances, no? So using our uh, delta to y conversion, okay, we obtain the y equivalent reactances, no, of those impedances connected between, okay, bus 1, okay, bus 3, and okay, bus 4. So this is the equivalent y, no, after solving. And then from this, we can see that, okay, this reactance of generator 1 will now be in series with this reactance, okay, connected to bus 1. Okay, and then also, okay, this reactance of generator 2 would be in series now with this reactance, no? And then from this we have, okay, we have this reactance, okay, connected to bus 3. So we combine these two, and so we have, okay, this one is still this, but this 2 is now equal to J.39, okay, 52, and these two, okay, are equal to the total of point, okay, 36, okay, 73. Now with this, okay, voltages na for V1 and V2 with the same voltage magnitude, no, of 1.0 per unit. So the to get the Thevenin's equivalent reactance for this network, now we have to short the voltage sources. Shorting this and shorting this. We'll only have this reactance parallel with this. So uh, the result would be okay. mm, this one. Okay. Now this is the parallel combination of this one. So after combining, we restore the voltage of our generator. Now we only represent one voltage here, because anyway the voltage generator 1 is equal to the voltage generator 2. So we can just combine them together with a per unit value of 1.0. So then with this equivalent reactance of the two, now this will now be in series with this reactance here. So which we can add now because they are in series. So the total is J.26 18, and then we have here the generated voltage of 1.0 an angle of 0. So do not be confused that since we have two voltage sources here and here we have only one, so it doesn't actually matter, no, because our voltage here is the same or has the same value as the voltage of each in its case here, no. So with respect to bus 3, where we just call this as point F1, because this corresponds to the faulted point, no, at point F, for positive sequence. So we call this as F1. So this whole thing now is now the simplified equivalent circuit for our positive sequence network. Now, so in the coming examples or in the succeeding examples of problems, when we simplify the positive sequence network, we are expecting to have a generated voltage here to represent the generated positive sequence voltage generated by the generator, and the total equivalent reactance between the point of interest, no, or at the point of fault, and the neutral or reference bus, which is which we just call as in1. So this thing here, no, it would be our the positive equivalent positive sequence network in the most simplified form. Now for the negative sequence network, well, we have seen in the previous example that this is the case. Now with no generated voltage here for generator 1 and no generated voltage at generator 2, and we have the connections now of the transformers and the lines here. And now we will be again looking at the network with respect to bus 3, where we assume that there is a fault here. So again, with respect to this bus, we cannot combine this and this because we are going to consider bus 3, no, as the case where we have to study, perhaps the amount of fault current at this bus. So we can only combine these two at the left, and at the bottom also we can combine these three because they are in series. So the resulting network then would be this one. So at the this is now our bus 3 with F2 as the point of interest, because this is where the fault occurs, no? So for negative sequence, we just call this point as F2, uh, meaning the point of fault when we consider the negative sequence network. Now at the left we have this equivalent impedance. Now the sum of the two. Okay, so we have 0.35, and then at the right we still have this 0.3, and then at the bottom we have three reactances before. So their sum is 0.82, and this is for generator 1 and this is for generator 2. Now again, with respect to bus 3, bus 1, and bus 4, okay, we have formed here, okay, delta connected reactances. So again, we obtain the Y equivalent reactances now for this with respect to bus 1, bus 3, and bus 4. So in effect, okay, after the conversion, we have the value here connected to bus 3 of 0.0714, and the reactance connected to bus 1 as 0.1952, and the reactance connected to bus 4 as 0.1673, and we have the reactance of generator 1 and the reactance of generator 2. So now, we can see that these two can be combined because they are in series. These two also can be combined if they are in series. So we have this, no? J.3352 as the sum of these two, and J.3073 as the sum of these two. So we have these two, and then we have that one, and then we have seen that these two are in parallel. So we can get the equivalent reactance of this. So uh, getting the equivalent reactance, so you have this 1.1603, and then we have this 0.0714, and so they are in series, so we can combine them together. So we have total reactance of 0.2317. So with respect to F2 and the reference neutral into, we have only the reactance here, no? Total reactance of 0.2317. Okay, so this is our simplified equivalent network for the zero sequence of our network. Now for the zero sequence network, we have seen last time that we have this connection, no? Because of the uh, connections of our transformers. Okay, for a transformer T1, again, okay, because it is YY connected and grounded both sides, so zero sequence current can just flow from bus 1 to bus 2, and then we have here a TL to 3. And then for transformer 2, okay, we have YY ungrounded. So YY ungrounded, so at the primary, it's open, and in the secondary winding it is also open, so open. Now for a transformer 3, so YY grounded, okay, both sides. So again, a zero sequence current can flow here, okay, between the primary terminal and the secondary terminal. And then we have also transmission lines where zero sequence current can also flow between bus 5 and bus 6. But for transformer 4, where we have delta-delta connection, so we have this equivalent circuit, no? Uh, for the primary winding, it is open, and at the secondary winding, it is open. And then because we have delta at the primary and delta at the secondary, so the zero sequence current will just circulate, no? So we represent our circuit as this, so meaning circulating currents may be flowing here. It cannot go out to the primary or to the secondary terminals. Now looking at this zero sequence equivalent network, we see that with respect to bus 3, we want to trace the circuit which has a complete connection from bus 3 towards the uh, reference axis in O, no? So here first we start going to the right. So zero sequence current cannot flow here, so no current can flow. And then this is open, so no current can zero sequence current can flow at this side, right? Now, so no, so we do not worry about this reactance here, because we just don't have zero sequence current flowing at this side. Now, again, we go to the left, no? From bus 3, okay, zero sequence current, okay, may flow through this, okay, to bus 2, and then from bus 2 to bus 1, okay, zero sequence also, okay, may flow. And then from bus 1 to bus 5, okay, zero sequence may flow. And from bus 5 to bus 6, zero sequence current may flow. But from bus 6, okay, to bus 4, we see that the zero sequence current cannot flow. Okay, so therefore, okay, from bus 1 to bus 6, okay, no current, no zero sequence current can flow here, no, because we have here open. So therefore, from bus 1, if we continue tracing the flow of the zero sequence current, okay, the zero sequence current can flow, no, from bus 3, okay, going to bus 2, then going to bus 1, and then to the reference axis in O through this. So we have only therefore this path now for the zero sequence current. So our equivalent circuit therefore from okay, bus 3 would just be equal to this, no? J.03, and then we have okay, J.2 for our transformer, and then okay, J.06 for our generator 1. Now we see that these three reactances are in series, so we can just add them together, no, to represent our equivalent impedance, which is J.56, and this is NO. And by the way, this should have been our FO, no? FO. So this thing here will just represent the zero sequence, okay, network, no, of the given network.